Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. We are in the process of learning how cryptocurrencies mimic the properties of fiat money. In this lesson, we will learn what is double spending and how is it prevented in cryptocurrencies. We will then review a couple of scenarios where double spending can occur in cryptocurrencies. Before we proceed further with this lesson, let us take a moment to orient ourselves on where we are. We have been learning about how cryptocurrencies mimic the four properties of currency. We will now cover the fourth and final property of fiat money, namely that you cannot double spend it. Assume Alice has $50 in her bank account. She cannot pay the $50 to both Bob and Harry. The reason is that when she pays $50 to Tom, the bank updates the record to reflect that she has zero balance. In fiat money, double spending prevention is achieved via a central record keeper, in the form of a bank. In cryptocurrencies, there is no central record keeper. However, there needs to be an alternative way to prevent double spending. To learn how a double spend is prevented in Bitcoin, we will set up a scenario. To keep things simple, we will assume there are 5 mining nodes. The remaining nodes are all non-mining nodes. Alice is a buyer of jewelry. She runs a non-mining node on the blockchain. Bob and Tom are jewelers who accepts Bitcoin payments. They interact with the blockchain via wallet software. In the setup, let us assume 3 blocks have been mined in the network so far. We will first sketch the happy path on how double spending is prevented. Alice creates 2 transactions paying 1 Bitcoin to Bob and paying the same amount to Tom. Both refer to the same UTXO. A wallet software is likely to prevent users from initiating the second transaction with the same UTXO, but since she is running a node, there is no intermediary to prevent her from sending these 2 transactions to the blockchain. Both these transactions enter the mempool of each node on the blockchain. One of the transactions, the payment to Bob, gets mined into block 4. When the payment to Tom is sought to be mined into block 5, it is rejected by the miner because the UTXO is already spent. To summarize, double spending is prevented in cryptocurrencies because a transaction that references a pre-used UTXO is not mined into a block. A transaction that is not included in a block is effectively void. So far, we discussed the happy path. But does this mean that double spending can never occur? There are scenarios that are unlikely but theoretically feasible. The goal of this lesson is not to explain every possible circumstance where double spending might occur. But to get a flavor of why it is unlikely, we will cover a couple of scenarios. The first scenario we will cover is that of a double spending through a soft fork. The second scenario is that of a 51% attack. We covered soft forks in the previous lesson. In case it has been a while since you covered the previous lesson, this would be a good time to revisit it. It will be easier to understand the upcoming discussion. Once again, the setup is the same. Alice sends 1 BTC to Bob and 1 BTC to Tom simultaneously. Now miner 1 and miner 2 chance upon the golden nonce near simultaneously. The payment to Bob is included in block 4B mined by miner 1. The payment to Tom is included in block 4T mined by miner 2. Some nodes receive block 4B first and some receive block 4T first. Below is what the blockchain looks like for each node. Node 1. Block 1, 2, 3 and 4B. Node 2. Block 1, 2, 3 and 4T. Node 3. Block 1, 2, 3 and 4B. When it receives block 4T, Node 3 rejects that block because he cannot have 2 blocks referring to the same block 3 as parent. Node 4. Block 1, 2, 3 and 4B. Node 5. Block 1, 2, 3 and 4T. It so happens that Bob and Tom's wallet is linked to Node 1. Bob believes that he has gotten the payment and ships jewelry to Alice. Tom cannot see a payment. Hence, he does not ship any goods. Next, block 5 is mined by Node 5. Node 5 thinks that block 4T is the last mined block. Hence, it mines block 5 referencing block 4T as parent and propagates the block to all nodes. When block 5 arrives at node 2, there is no problem. It is just added to the blockchain. But nodes 1, 3 and 4 were expecting block 4B to be the parent of block 5. There are 2 versions of the blockchain confronted by nodes 1, 3 and 4. By the longest chain rule, they accept the blockchain which has block 4T as the parent of the 5th block. We can now see that the payment to Bob is now not part of the official blockchain record. It is as though it never happened. Bob now checks his Bitcoin wallet and sees that the earlier payment has vanished. He is out of both the jewels and cash. We noted, earlier, that both Bob and Tom's wallet are connected to Node 1. Tom can now see that he has received funds and ships his jewels to Alice. Alice has successfully double spent. In our example, Bob could have waited till Block 5 was formed till he shipped his goods. But what if Block 5 also had the simultaneous block creation problem? This is highly unlikely given the probabilities involved. But for the abundance of caution, Bob could wait for the next 4 blocks to be mined, before shipping the goods. Number of confirmations refers to how many blocks have been built on top of the block that contains a specific transaction. For abundance of caution, users are recommended to wait for 4 confirmations till they assume that payment has been received. After 4 confirmations, it is virtually guaranteed that any soft forks will resolve themselves. Now that we have reviewed the soft fork example, let us pause to reflect on this. An accidental soft fork occurs when 2 miners successfully mine a block at the same time. In earlier lessons, we learnt that guessing the golden nonce has a low probability and requires billions of iterations. Hence, accidental soft forks are not common to begin with. The ability of a malicious double spender like Alice to cause a soft fork in a way that her 2 transactions end up occurring in different blocks is not very high. However, the scenario envisioned can occur, and hence waiting for a few confirmations is a good practice for anyone receiving Bitcoin payments. We will now cover the second scenario of a 51% attack. In this example, Alice runs one of the mining nodes, say mining node 1. She creates a transaction sending 1 BTC to Bob. The transaction enters the mempool and is mined into a block. Prior to this transaction, 3 blocks had been mined. So now a 4th block is added to all the nodes. Let us call this block 4T, where T stands for truth. But Alice does something else. She mines a block on her own computer. This block excludes the payment she made to Bob.
We will call this block 4F, F standing for false.
Alice does not propagate the block to anyone else. The blockchain continues to be formed. Block 5T assumes block 4T as the parent. Block 6T assumes block 5T as the parent. However, simultaneously, Alice is mining shadow blocks. Block 5F, block 6F and so on. But she does not propagate the blocks to others. Bob sees that he has received 1 BTC in his account and he ships the jewelry to Alice. He sends Alice the FedEx tracking number. On checking the FedEx tracking number, Alice is able to confirm she will get the jewels next day. At this point 8 blocks have been mined. Alice now mines the 9th block. But Alice propagates the 9th block to all the nodes on the blockchain. We can call this block 9F because it refers to block 8F. The blockchain that the other mining nodes have is T-series. But now they are confronted with the F-series. The F-series is longer than the T-series. Hence, all nodes switch to F-series. The blockchain network now reflects the F-series. It no longer has the payment to Bob. Bob is out of both jewels and cash. Why is this called the 51% attack? The attack part refers to the attack on the rules of the blockchain network. But why 51%? For Alice to succeed in our example, Alice needs to replace the true blockchain with her shadow blockchain. In our example, she achieved this with block number 9. Even if this did not occur at block 9, at some point, she outcompetes other miners, so that her chain is the longest. This result can only be guaranteed if she has majority of the mining power of the network. Otherwise, there is no guarantee she will be able to form a block ahead of others. Assume a malicious miner assembles a set of powerful computers. These computers iterate the nonce very fast. To succeed, the computing capacity of this mining hardware must be greater than the mining capacity of all other miners. This means that this miner can guess the golden nonce faster than everyone else. Now that we understand the attack, some reflections on the cost of the 51% attack. First, there is the energy cost of mining the shadow blocks. Since the real blocks are mined every 10 minutes, the malicious miner must keep mining blocks at the same pace. Otherwise, the shadow chain won't be longer than the real chain. Second, the longer the malicious miner waits for superseding the true blockchain with the shadow blockchain, greater is the cost because she needs to mine a larger number of shadow blocks. Third, for the superseding other miners at the end of the shadow chain, the malicious miner must outcompete the mining capacity of all other miners combined. But in a scenario where there are thousands of miners, some of whom may be industrial-scale mining companies, this is very expensive. The energy costs of running such an operation will be prohibitive. Now, let us reflect on the benefit side of the equation. For this kind of scam to be worth executing, the benefits must outweigh the cost. First, the item delivered against the payment must be very expensive. This doesn't make sense for double spending on a Starbucks coffee. Second, for extremely high-value transactions, most sellers may deliver with greater lag. For instance, say someone was selling a painting worth $10 million. Theoretically, If the seller delivers 24 hours after payment, the malicious miner has to mine 14,400 shadow blocks. Finally, in the previous example, it may well be worth it to launch the double spend attack for a $10 million delivery. But in the real world, for such high value, low frequency transactions, the use of cryptocurrency for payment is likely to be accompanied by other checks and balances. We discussed two scenarios where double spending can occur: the soft fork and the 51% attack. People have proposed other scenarios where this can occur. We are not going to resolve the issue on whether cryptocurrencies can be double spent in this course. And that is not the point of this discussion. The takeaway here is that cryptocurrencies, like fiat currencies, cannot be easily double spent. This is achieved through technology instead of reliance on central counterparties. Whether the preventability of double spending is 100% foolproof is a matter of debate. But the likelihood of occurrence for established cryptocurrencies like Bitcoin and Ether is very low. We have been learning about how cryptocurrencies mimic the four properties of currency. We have now covered all four properties. This also brings us to the end of this lesson. Review the summary of this lesson before proceeding to the next one.